Alright, I stopped the previous vodcast at this point because it's a different sort of problem. We haven't actually talked about it yet. Having said that, you have done these types of problems before, or at least you have the theory for it. Notice what it says, find to 3 decimal places. That's going to be important in your answer to do that, 3 decimal places. And it wants you to find the gradient. Well, we've already done gradients, it's the rise over the run. But here's the different bit. It says it gives you the angle of inclination to the x-axis. What does that mean? Well, if we have our axes like so and like so, you know which one's the x-axis, of course. Oop, did the wrong thing there. So there's your x-axis, there's your y-axis. Now it says the angle of inclination to this one here, to the x-axis. So that means for this particular problem here that the angle of inclination to the x-axis, let's put it in there, so there's the line, that this angle of inclination here to the x-axis is 37 degrees. Let's leave that, shouldn't have bit that bit there. So that's 37 degrees. So what's the gradient of this line? How do we do this? Well, what's the gradient again? It's the rise over the run, isn't it? Rise over the run. Now look at this triangle here. If I drop a line down there, I've actually got a right angle triangle. And I know an angle to it. And now we know about SOHCAHTOA. We've done all this before, you have. And remember what all this means? Sine, opposite over hypotenuse. Cos is adjacent over hypotenuse. Now tan is opposite over adjacent. Now watch this. So the tan is the opposite, that's this side here, over the adjacent. Now notice what we said about gradient, rise over run. So the rise, that's actually that length there, isn't it? So the opposite side is equal to the rise. And the adjacent side, well, that's really equivalent to the run. So since tan equals opposite over adjacent, this is exactly the same as rise over run. So the tan of an angle, whatever the angle happens to be, is equal to the gradient. Did you know that? Well, you do now. So there we go. So this particular case, the gradient is equal to then the tan of 37 degrees. So for A, the gradient of the line, and that's all you're asked to do is just find the gradient of the line, is equal to whatever tan 37 degrees happens to be. I'm not going to work that out, you just get your calculator out, tan of 37, but note it's to 3 decimal places, and so that's how these particular problems are done. Question 9 and 10, well, I put them together because they're related. We have to find the exact gradient, it says, of this particular line joining these points. So, you know, if we were to do a really quick graph, 4, 7, you know, where's that going to be? Cross 4, up 7, somewhere around about there. What about this one? 3, 6. Okay, well there and up a little bit less, so something like that. So it's saying, what's the gradient then of that line there? Well, again, you're just going to take these points and you're going to work out the rise, which is from 6 to 7, and then the run, which is from 3 to 4, so that's 1 over 1, isn't it? So we can see that the gradient, which is what we're asked to find out of that one, is just equal to 1 over 1, so it's equal to 1. So that's the first part. And the angle of inclination, well, here, if it wasn't obvious because it's 1, we'd have to write, well, we don't know what it is, so the tan of whatever the angle is equal to 1. Now remember, if we want to know what theta is, we have to work out the inverse sine. So the inverse sine of 1 is equal to theta, and that happens to be equal to 45 degrees. But you can use your calculator to work out the inverse tan function. So that's all I asked for question 9, but question 10 asks you now to find the equation in that form, y equals mx plus c. So we know the gradient, we've got that, and we've got 2 points. So for this particular one, for question 10, finding the equation, we'd say, okay, well look, we've got the gradient, it's equal to 1x plus c, and now we need to, so that's the gradient there, which is given by that. So now what do? Well, we can take either of these points, because that is x and that is y, and put those in this equation. So if y is 6, when x, well, I'll leave the one there, we didn't have to write it, but anyway, I'll do it. When x is 3, then that's our situation. We can now use this to work out what c is. So c is equal to 6 minus 3, which equals 3. So our equation is y equals x, just 1x, I'm just going to write x, plus 3. And that's our particular equation. So that's how we go about doing these ones. The next one, look very similar, just got different mixes of things. This is, well, tells you the gradient and the y-intercept, so that should be very easy to work out the equation y equals mx plus c. This one gives you the x-intercept though, not the y-intercept, so we need to work out the y-intercept. So we've got an equation which has a gradient of 3, up 3, across 2, here, goes through where, we don't know, but we do know that it goes through x is 4, so it's going to go where? Don't know. We only know that it was on this point here 4. From there we'll actually go up 3 and across 2, and from there we'll be able to actually work out the line and work out where that goes. Well, I'll do that properly later, but that should give you a hint as to how to go about it. And so on. Angle of inclination, that lets us work out the gradient, and so on. In this problem here, find straight lines, exact values. Well, look, this is nothing new, just more complicated. The only thing is, the y isn't just 1y, it's 3y or 4y or 5y. So we need to rearrange this equation with that in mind. So let's just take this one here. So you've got 2x minus 3y equals 6. So I'm going to add 3y to both sides, because in that way we'll end up having our y as positive. Then we'll take away 6 from both sides, so you'll end up with that, and that's where the 3y comes in, where we need to divide both sides by 3, divide everything by 3. So we divide this by 3, we divide the 6 by 3, and we divide this by 3, and that's then the final end of our actual equation. This one here I'll do as a separate vodcast because it's involving the graphics calculator.